Hello friends, welcome you all in this video lecture session where we will discuss the basic of the nuclear magnetic resonance. In short, this is called NMR. Actually, this subject deals with a nuclei which in presence of an external magnetic field are susceptible to resonate. If we consider these three blue colored things, this word nuclei in magnetic M and the resonate R all brings together the word NMR. Actually, for complete and the concise description of NMR, it requires a quantum mechanical approach. However, we are using a semi-classical model which also provide a rational understanding of the NMR. Friends, I'm sure all of you are very much familiar with the term called atoms. These atoms have basically two parts: the nucleus, which consists the proton, the positively charged species, the neutrons, which is neutral, and the electrons, which are revolving around this nucleus. If you want to compare this structure of the atom, you can easily compare this with the solar system, where sun is acting as a nucleus and the planets, they're revolving around the sun. So in a word, we can say the nucleus, this is nothing but a positively charged, and these nucleus, like the electron, they are also spinning. And due to the spinning motion, they are generating basically a spin angular momentum. The spinning motion of the nucleus are of two types. If you see this thing, you will find one is clockwise and another one is anti-clockwise. In the clockwise and anti-clockwise, which we can designate as alpha and beta, when they are moving or spinning, they will generate the spin angular momentum, and this spin angular momentum Ls is quantized in the unit of h cut. In the mathematical form, we can write it Ls equal to I h cut, where I h cut can be written as a I dot h by 2 pi. H is nothing but the Planck's constant. Here we are introducing a new term, that is I, the spin quantum number. I'm sure all of you are very much familiar with the four quantum numbers of electrons: the principal quantum number N, azimuthal quantum number L, magnetic quantum number M, and the spin quantum number S. Like that spin quantum number of the electrons, the nuclei have also the spin quantum number I, and these basically describe the symmetry of the nuclear charge distribution. In a nutshell, we can say the nuclei which are positively in charge, they are possessing a spin angular momentum, and this spin angular momentum is basically a quantum mechanical property. So now we should learn a little bit about the spin of the nucleus. The spin, a quantum mechanical property, can be written, I have already said that I is equal to root over of I into I plus 1 into h cut. Here h cut is equal to h by 2 pi, where h is the Planck's constant. And the I, this is basically a characteristics of all the nucleus, and depending on the particular nucleus, I has different values. Mainly, this is two type. One is the zero and the second one is the non-zero. And the non-zero can be further classified into two parts. One is the integral and the second one is the half integral. The spin quantum number is simply referring to the total spin of the nuclei. So that means when we are considering the spin quantum number, it is basically the sum of the spins of the proton as well as the sum of the spin of the neutrons. So depending on this I value, we can have, these are the different types of the nucleus. For even number of proton and even number of neutron, that is like C612 or carbon 12 6 or oxygen 16 or 8O16, where both the proton and the neutron number are positive and even they are producing I is equal to 0. For the nuclei like 1H1, 13C6 or 15N7, they have the spin value I equal to half. Here, if we say that thing, in 1H1, there is a 1 proton is there and there is no neutron. But in 13C6, where the 6 proton, that means the even number of proton, and the 7 neutron, that is the odd number of neutron is there. But in case of, if we have both odd, that is like 1H1 isotope, which is called the deuterium, that is 2H1, here 1 proton and 1 neutron is there, both have the contribution of half and half, and overall spin we are getting 1. So once again we can say the I is the characteristic property of the nucleus, and the rest is the basic key part of the NMR. So this, once again we have to see the, when we will see this I half, that is spin equal to half for this nucleus, the nuclear charge distribution is spherically symmetric. But one thing we have to consider, the natural abundance. Why? Because as we are talking about the chemical compounds, or we are talking of the biological samples, where we have to look about the hydrogen, where we have to look about the carbon, or we have to look about the nitrogen. This is very important. Hydrogen has a 100% of the natural abundance. It is precisely 99.98%, whereas carbon 13 is 1.07. But the nitrogen 15 is even less. This is 0.367. Now, if we again go to the electron system, where we find that there is an azimuthal quantum number, when they are placed in external magnetic field, what they will find? They will find a Zeeman effect. And this splitting is occurring basically 2I plus 1. So similarly here, in this particular case, the nuclei having the definite spin angular momentum Ls not equal to 0. Why? Because Ls equal to I H cut. So I equal to 0, Ls equal to 0. But for this particular case, where Ls equal to non-zero, so when they placed in the external magnetic field H0, they must possess a definite spin magnetic moment. That means this particular spin magnetic momentum mu s, which is basically equal to gamma into Ls, equal to gamma I H by 2 pi. That means if you have an I equal to 0 for spin 0 nucleus, the mu s equal to 0. That means they have no external effect on the H0. But where again we are introducing a new term, that is a gamma, which is called the gyromagnetic ratio, and this is a characteristic property of the individual nucleus. The gamma, if we consider the gamma of the proton, and if we compare the gamma of the 13C, the gamma of the 13C is basically the 1/4 of the gamma of the proton. Now, the magnetic quantum number, how it behaves in external magnetic field. So when the spin quantum number I is placed in the external magnetic field, it will split into 2I plus 1. I have already told you, like the electrons, the azimuthal quantum number, when they are placed in external magnetic field, they will basically see the 2L plus 1 splitting. If you have a p orbital which has the electron, actually the spin which has the azimuthal quantum number L equal to 1, in presence of the external magnetic field, its magnetic quantum number is -1 0 plus 1. So that is 2 into 1 plus 1, And here we are getting similarly 2I plus 1. So for the spin half nucleus like 1H1, here we will find there are two type of splitting. One is I minus half H dot and the another one is plus H. Whereas in case of the deuterium where I equal to 1, we have 2 into I plus 1, and this 2 into I plus 1 means 2 into 1 plus 1 is equal to 3. So once again, this is simply recapitulation of all the previous slides. So for mu equal to gamma into Ls, that is I must be equal to non-zero. That means nuclei with a definite spin angular momentum Ls values when subjected to the external magnetic field must possess a definite spin magnetic moment. And this is very essential, as this nucleus in that particular system will behave nothing but a tiny magnet. And this tiny magnet I is quantized. Accordingly, also magnetic moment mu is quantized. And when such the tiny nuclear magnet or the nuclei are placed in external uniform magnetic field H0, they assume certain discrete orientations, which I have already discussed, and this will take 2I plus 1 orientations. For hydrogen, I have already told you, for carbon 13C, with the spin number I equal to half, it will split into the two discrete energy level in presence of any external magnetic field. And now, anything, when we are comparing whether a reaction will take place or not, whether a system will go here to there or not, the energy is the coin. So, energy is very important, and energy of the magnetic dipole in the field we have to consider. So, how? Because I have already told you that NMR or the nuclear magnetic resonance is an example of absorption spectroscopy. And it has basically two types of spin. At the ordinary condition, the two spin states, alpha or beta, which we are designating either clockwise or anti-clockwise, they are degenerated. But once they are placed in the external magnetic field, a splitting occurs, and due to the splitting, their energy perturbation takes place. And this splitting basically causes two types of things. Already we have known basically from half, I equal to half, we have 2I plus 1 equal to two energy states. One is going down and the another one is going up. Going down means going down from the very center, or we have to say that from the initial states. And here in these particular states, if we consider the lower part, this one is basically have the spins, and these spins are basically either parallel spin or the anti-parallel spin. For those, the ground state energy system, those ground state energy system, the nuclei which are present, they are basically the parallel to the external magnetic field, whereas the higher energy system, they are anti-parallel. But once they will acquire this particular difference energy somewhere, and that is the difference energy is in the radio frequency pulse. This radio frequency will give the system, and then we will find that in ground state electrons or the ground states, the spin will go up, there causes a spin flipping, and this spin flipping is basically giving the resonance. So how friends, I think now you understand the three parts. So first part is the nuclei, I not equal to 0. The second part is the magnetic field, the external magnetic field H0. And the third one is resonance, that means the difference which we will find in case of the radio frequency when it goes up. However, once again, I have to say that when there is no H0, the delta E, the difference is 0. But once we are applying the external magnetic field, with increase in the external magnetic field, the delta E, the difference in the energy states are increasing. So H0 has a very important role. And sometimes, somehow, I think you have heard about a 500 megahertz instrument. You have heard said about the 800 megahertz instrument. Also, you have heard about 60 megahertz instrument. So people, if we have a 60 megahertz instrument and if you have a 600 megahertz instrument, obviously in the 600 megahertz instrument, this delta E is much higher. That means the splitting is much higher compared to that of the lower magnetic field, that is 60 megahertz. Now, what will happen when these external magnetic fields are applied on this tiny magnet? Basically, unless these nuclear magnets are exactly parallel or anti-parallel with this external field, that means which nuclear we are talking about? We are talking about the tiny magnets where I is not equal to 0, and that means those nucleus are itself or themselves, they are a tiny magnet. And they are basically they are placed on a big XH0. And once and until and unless they are not exactly parallel or anti-parallel, there would be no transition. Rather, the spin flipping which we want, that is called resonance. So when this nucleus is placed in the uniform external magnetic field, the field will try to orient it along its own direction, for which the spinning nucleus suffers a torque. But as the nucleus itself possesses a definite spin angular momentum, it will actually precess. So if we consider this one like this is the z-axis and this is the nucleus, so that will precess like this. And this precession is called the Larmor precession, and the frequency related to this is called the Larmor frequency omega, which is equal to gamma H0. So that means this gamma, which is a characteristic property of the nucleus itself, and this H0, which is the characteristic property of the external magnetic field, depends on that the Larmor precession occurs. So once again, I have to mention that the nuclei is very important and also the magnetic field. Now, in a cartoon representation, we can see in this way. This is the all spins are happy. They have the degenerated alpha and beta. There is nothing. No discrimination is there. But once they are placed in the external magnetic field H0, there is basically difference in energy. One, those who are parallel with these H0, they are lowering in energy and suffering a comfortable situation, whereas anti-parallel spins, they are opposing like this one, and they are basically higher in energy. And in this particular case, if you can remember the previous slides where I have shown you, this is called the ground state, and this ground state where the nuclear spin must be higher compared to this one of the excited state. So the fundamental principle of the NMR spectroscopy is there must be small but an excess nucleus in the ground state. And these, once we consider, they call the bulk magnetization. This is the effective one. This is basically coming from the due to the excess spin which is coming from the excess number of nucleus. And this is basically aligned along the z-axis with parallel to H0. And this is the overall spin. This is the anti-parallel and this is the parallel, and overall the mz is there. So we call it a z magnetization. And this is showing you how the all spin is converted into the z magnetization. So once again, we have to go, that is the torque of the tiny magnets and torque between the external magnetic field and then the internal motion. There gives a precession, and this precession occurs around the z-axis as H0 is placed along the z-axis. And due to this precession, a Larmor frequency is generated, and this Larmor frequency omega, it depends on both the nuclear property gamma and the H0. Here I must mention one thing. If we compare the gamma of 1H1 and if we compare the gamma of 13C6, there the 13C6 gamma value is 1/4 of that of this one of the 1H1. So When we are talking about a spectroscopy, that means we have to supply some energy. And I have already shown you that there is a difference in energy between the ground state and the excited state. And this amount of energy, this is the electromagnetic radiation, which considers all kind of systems. And out of this particular radio frequency zone, that is 10 to the power 6 or to 10 to the power 8 hertz, is basically called the radio frequency. And this is basically important for the spin flipping. That is, all NMR is there. There are other also there. But the energy difference, the most interesting part of this thing is energy difference between the two energy states are extremely small. So this method is very insensitive. However, lines are narrow, resolutions are very high. So how you have to compare this? I hope everyone have an idea about the electronic spectra, that is UV visible spectra. This UV visible spectra is broad, but in case of the NMR spectra, the lines are narrow. In case of the UV visible spectra, we have to see that the energy difference between the ground state and the excited state are very high, that is 10 to the power 16 hertz. Whereas this is very low, 10 to the power 6 to 10 to the power 8 hertz. But the spectra of the NMR can depend on interaction between these observed nuclei, that is the structural orientations. And we have this. So in a nutshell, this is the whole cartoon picture of this, where we find this is the magnetic coil and which is perpendicular to the magnetic field, and in presence of that, this is the spin, the Z magnetization of the nucleus, which is parallel to H0. And once they are having like this is like this, the 90-degree, and this is giving you a pulse, the radio frequency pulse appropriate. It goes from here to it goes there, along from the Z axis to the Y axis, and here the detector is there. And this detector, once you switch off the RF pulse, it will come back to its original position. And this is called the relaxation. And that is occurring the free induction decay. So once it is in the 90-degree, this is the signal in the time domain. And this NMR signal is now transferred to the Fourier transformation, and we are having the frequency. So this is giving the signal, and we are depending on the omega, that is the Larmor precession frequency. So friends, I am sure that we have understand what is the role of the nucleus. I am sure you have also understand what is the role of magnet and how these two comes together for resonance, and why the subject is called NMR or nuclear magnetic resonance. Now the question is why one should learn this NMR. Basically, this helps us in identification of the molecular structure. This helps us in understanding the reaction pathways. This helps us in elucidation of the 3D structures of the macromolecules like proteins, nucleic acids, etc. The study of protein-protein and protein-DNA interaction is possible or feasible by using this method. Understanding the protein foldings, and mainly, which is very important, is the healthcare. We are very much familiar, we are common. This today is called the MRI. The full name is magnetic resonance imaging. So friends, today up to this, I hope you enjoy this session, and we will learn a new thing in the next day, when we will call or we will understand how this NMR signal is used to understand what is the structure. So today, happy NMR.